In this video, I will be deriving the equations to simulate the change in concentration with respect to time and change in temperature with respect to time of a constantly stirred tank reactor. So here we have a tank reactor with a set volume, and it's constantly being stirred. There's also a cooling jacket around the reactor that will cool the contents of the reactor as the reaction takes place. So there is a temperature inside the reactor, and there's also the temperature of the coolant. Additionally, we'll have a flow rate into the tank, which is given as Q. It equals 100 liters per minute. Since it's a constant volume reactor, the flow rate in will be equal to the flow rate out. There's also the concentration of A going in for our reaction. So our reaction is a first order reaction from A to B. We can get at the rate of this reaction by using the Arrhenius equation, which the rate will be equal to our rate constant, which we are given in the problem, times exponential function of the negative activation energy over R times temperature. So we are given the activation energy over R as 8,750 kelvins. So we can rewrite this rate as the rate constant times the exponential function of negative 8,750 over temperature. And then we can use this to get at the rate of our reaction, which, since it's a first order reaction, will just be the rate of the reaction, K, from the Arrhenius equation, times the concentration of A. So using this and the flow rates in and out of the tank, we can calculate the change in concentration with respect to time. So this will be equal to the concentration of A in minus the concentration of A that's flowing out, minus the rate that A is being used up by our reaction. So to get at the rate that the rate of A that is going in, it will be multiplied by Q, which is our volumetric flow rate in, times the concentration of A into the tank. The flow rate or the concentration of A leaving the tank can be expressed as the volumetric flow rate out of the tank, which in this case is Q again, times the concentration of A in the reactor. Now, we also have the rate at which A is being used up by our reaction, which is our rate, which is our reaction rate times the concentration of A, and this is on a per volume basis, so we have to multiply by V. Now, we can divide both sides of this equation by volume and rearrange it to get the rate and change of our concentration with respect to time. This will be equal to our flow rate over the volume of the tank times the concentration of A going in minus the concentration of A in the tank minus the rate at which A is being used up by the reaction. Now we need to get the equation for the rate and change of temperature. So we'll do this by expressing it as a energy balance. So we need the total internal energy of the tank. We are given the specific heat capacity, just a single specific heat capacity, so we can assume that this applies to everything in our system. So this is given on a per mass basis, so we need to get the mass inside of our reactor. We can do this by using the volume and the density of the reactor. So the density was given as 1,000 grams per liter times the volume. This will give us the mass in our tank. And to get the total internal energy, we'll multiply by the specific heat capacity and the change in temperature with respect to time. And this will be equal to the total enthalpy in minus the total enthalpy out And we also have a rate of heat transfer between the contents inside the reactor and the cooling jacket. So we're given a transfer constant of UA, and we can express the heat transfer between the cooling jacket and the reactor by this constant times the difference in temperature between the cooling jacket and the contents in the reactor. So the bigger the difference in temperature between the cooling jacket and the reactor, the faster the heat will transfer to the cooling fluid. So now we need to get at the enthalpy, the change in enthalpy of the system. So this comes about in two different parts of the reaction, or two different parts of the system. I'm just going to copy down the left side of the equation. And so the first part we need to take in account is the difference in temperature going into the tank and temperature leaving the tank. So we have a temperature in minus the temperature out. And since it's a constantly stirred tank, the temperature in the tank and the temperature leaving the tank will be equal. So now we can multiply this by our specific heat capacity, and again it needs to be in a per mass basis. And so we will multiply our flow rate by the volume of the tank to get it in a per mass basis. The second part of the change in enthalpy is the heat added by the exothermic reaction of A to B. So this is just our reaction rate, which is our reaction constant K times the concentration of A. Remember, it's on a per volume basis, so we have to multiply by the volume of our reactor. And to get the change in enthalpy because of this reaction, we will multiply by the change in enthalpy per mole for this reaction, which is just negative delta HR. And we are given this in the problem. And then again, we still have the rate of transfer of heat between the reactor and the cooling jacket. So now I will use both of these equations to simulate the behavior of this system in Python.